In this video, I will outline a machine learning algorithm our lab is actively working on to improve the speed and accuracy of electric field measurements using Rydberg atoms. Rydberg atoms are neutral atoms where the electron is in a highly excited principal quantum number state. These Rydberg states have strong electric dipole-dipole interactions that are widely used for neutral atom array quantum computation and quantum simulation experiments. These strong electric dipole moments make Rydberg atoms excellent electric field sensors. Unfortunately, this extreme sensitivity is also a weak point. In a real experiment such as ours, slowly moving patch charges on the outside surface of our vacuum chamber are enough to shift our Rydberg lasers out of resonance. Therefore, it is critically important to minimize stray electric field fluctuations and to engineer an active control over the electric field environment of our atoms. However, ordinary measurement techniques are time-intensive and reduce measurement sensitivity. A solution to this problem is to use a combination of Bayesian inference and machine learning to rapidly measure and eliminate stray electric fields using electrodes inside the vacuum chamber. Let's zoom into the central trapping location of our atoms in our glass cell. Shown here is a rubidium motte inside a Faraday cage composed of 6 addressable electric field plates. Our atomic arrays are generated by loading individual atoms from this bright fluorescent gas into individually addressable optical tweezers. Here's an image of 225 of our atomic qubits spaced apart in the lattice by roughly 5 microns. I will now illustrate how our machine learning protocol will work on a single atomic qubit. The protocol I will outline to you has similarity with Hamiltonian learning algorithms, in particular the magnetic field learning protocols used in the NV Center community. We begin first by modeling the Hamiltonian of our system as h of e, where e indicates the value of the electric field. We assume that our optimizations begin with a reasonable guess at the probability distribution for the electric field, which we call P of E. From the distribution of the probabilities for the electric field, we can calculate an uncertainty for the electric field, which we denote sigma squared. A Ramsey interference experiment is then performed to measure the accumulated phase difference between the two quantum states of our atomic qubit. We measure the atom to be in one of two qubit levels, 0 or 1, which we call the outcome O. Immediately after measurement, we perform a numerical simulation on a toy model to estimate the probability of measuring the outcome O when the electric field and Ramsey pulse time are chosen as parameters. We can then implement Bayes' rule to update the probability distribution for the electric field. We then choose the next Ramsey pulse time to be related to the uncertainty of the updated probability distribution for the electric field. This entire sequence then repeats until the electric field uncertainty converges or reaches a predetermined threshold. Once we establish this method to rapidly measure the small electric fields in our chamber, we can then cancel them directly with the electric field plates to null them out or to apply an appropriate bias field. The pictures and data shown in this video are from the Bernien lab at the University of Chicago. In addition to using machine learning techniques to improve the sensing capabilities of Rydberg atoms, we are also investigating the use of machine learning tools to prepare large-scale entangled states and Hamiltonians at quantum critical points. Please feel free to send any one of us a message if you want to chat or discuss with us. Thanks for stopping by.